Now let's move to the next question. Question asks about the Roth's law and also Henry's law, the limitation of both. So here we just can define what is Roth's law and also Henry's law. For Roth's law is defined as the partial pressure of substance in a liquid mixture is proportional to its mole fraction in the mixture and its vapor pressure when pure. So given the formula of partial pressure of species A equal to SA, as SA is mean the mole fraction of A times with its vapor pressure when it's pure, while the Henry's law is the vapor pressure of a volatile solute B. Volatile solute is proportional to its mole fraction in a solution, given by PA or partial pressure of this A equal to SA. SA is a mole fraction, and so KKH is the Henry constant, or here, or where is the definition of Henry's law, where the concentration of species B equal to pressure of B at Henry constant. So when we talk about Roth's law is about when we have two species, species A and B. Each of it have its own vapor pressure, where when we add it together, when we add this one, so the vapor pressure will be modified a little bit. So we can use this relation, both relation, to define the modification of the species or the solution or the system. So for the limitation of heat, so according to this graph, we stated that here is a Henry's law and here is a Roth's law. We can see that near SB, or so if at this point the behavior will follow the Roth's law, and while at this point the behavior of a solution will will obey the Henry's law. We can say that when the solution are dilute enough for the solute to obey Henry's law, so when it's dilute, it's mean why it's mean dilute. Dilute is mean we have a solute, so we have solvent. So when we have a solute, when the solute is too small, so it will obey the Roth's law, while the solute is big, or when we have more solutes, we will have the solution will obey, the system will obey the Henry's law. So here is what is talk about Henry's law and Roth's law. The Henry's law and Roth's law is this law is about the quantity, or the quantity of between two species. When the solvent is more, we can use this law. When the solvent is more, we can use this law. So it's all about. The next question. Question 6. The question asks us consider an aqueous solution containing sodium chloride and HCl that has a density of 1.01 gram per milliliter. Assume the solution behave ideally. The freezing point of the solution at 1.08 m is minus 1.07 degree centigrade. Calculate the percent composition of the solution by mass. Given the cryoscopic constant equal to 1.86 and molar mass of NaCl, so the formula is 58.443. Okay, first, this is about the freezing point. It's about colligative properties. For colligative properties, when we add something, when we add a solute in our solvent a little bit, so it will change a little bit. It will change the properties of the solution, and one of it is the freezing point. So it will lower the freezing point. So we have the formula: Tf, or temperature at the freezing point, equal to Kf. Kf is constant, or we call it cryoscopic constant. And B is the molality. So Tf, we have this one, 1.07, and also Kf, we have this one given equation. So now we have B and NaCl. B is molality. Here is the molality. When we talk about molality, we will have 0.575. For what is molality? Molality is mole of solute per mass of solvent. Okay, so from here we can understand better where the mole of solute here is mole and kilogram. That's why we can state that what is meant by the 0.575 mole per kg. It means that we have 0.575 mole in 1 kilogram of water, or in 1 kilogram of our solvent. So in this case, we have water is our solvent. So that's why we already know the mole of solute. So next, what we need to do is we need to find the mole of solvent. So now we already know that if we consider this one, our water will be 1 kilogram. So we just use this value to find the molarity. To find the mole of water, or to find the mole of solvent. So here, as the question asks us about the mass. So the mass. So here we already know the mass of the solvent, which is 1 kilogram. So what we need to do next is we just find the mass of our solute. So here is our solute NaCl. We already have the mole. So if we have mole, we can find easily the mass of our solute, where the mole equal to mass over molar mass. Okay. So we just rearrange. So that's why we get mass equal to mole times molar mass. Our mole is 0.575, and our molar mass of sodium chloride, given in equation 58.443. So we put it here. So that's why we have 33.6 grams. So to find the mass percent of solute, mass of solute over total mass. So we have mass, this here is mass of solute. So for the total mass, we need to add we already determined the mass of solvent is 1 kilogram. So when we convert it to gram, it becomes 1000 grams plus 33.6, because it's total mass of our system, times 100, and we will have our answer. We will have 3.25%. Here is our answer. We calculate it, we have 3.25%. And then from this one, we can find once we have our solute, from there, if the question asks us about the solvent, So to find the solvent, it means that 100 minus 3.25%, and then we have 96.75% if the question asks us about the solvent. That is how you answer this kind of question. And then we move to the next question. Next question asks us about acetone and chloroform form ideal solution. Here is the keyword ideal solution. When mixed, boiling point for acetone and chloroform are 56.53 and 61.2 degrees centigrade respectively. The question asks us to sketch and label a thermodynamic composition diagram for the mixture. And also from the diagram, we need to determine the liquid and vapor composition. So, I already plot this one. So here we need to have a graph. We have one x-axis and two y-axis. So this one is temperature for chloroform. This one is temperature for acetone. Then here temperature. So from the question, should give us the boiling point for acetone. Here acetone is 56.53, so we plot here 56.53, and also the boiling point for chloroform is 61.20. So here we just sketch just like this, and we can have a diagram or a simple diagram of the visualization diagram for our mixture. And don't forget, so we need to determine this one is 0, this one is 1. So here is the mole fraction. The mole fraction of our here is where this one is the mole fraction. And from there, based on the diagram, compare the liquid and vapor composition of the solution prepared from 100 grams of acetone and chloroform each. So 100 gram, 100 gram. So we can 100 gram each. So we can say that this one is when we say 100 gram, 100 gram. So it means that it is 50%. So 50% is something like something here. You can plot this one. Okay, so the answer is you need to determine whether which composition is more liquid or vapor. So I determine this question for you. So you can refer, you can Google, you can discuss with your friend to how to determine the liquid or vapor composition. So your answer will be the liquid will be more than vapor, or the vapor will be more than liquid. So here is how you answer this question. You just need to determine from the graph either the liquid is more than vapor, or the vapor composition of more than liquid. So I will leave it to you.